Hi, and thanks for watching. Today I'll be talking to you about my PhD project regarding emergent collective behaviors for active particles with tunable interactions. But first, let me start by introducing myself. My name is Sandrine Heijnen, and I started in 2014 with a bachelor chemistry at Utrecht University. At the end of my bachelor, I really enjoyed working with colloids, and therefore I decided to continue with a master in nanomaterials. During my master, my main research project was to create chiral structures from superparamagnetic particles. This was done by first taking the superparamagnetic particles and aligning them with a magnetic field, and upon addition of a polymer to the system, which gives rise to the depletion interaction, we were able to form these ribbon-like structures. In 2020, I started my PhD at University College London within the ActiveMatter network. The ActiveMatter network has four main goals. First, to create biocompatible active particles. Second, to study self-assembly of active and living matter. Third, to understand emergent and synergistic behavior. And finally, to create real-life applications. My role within the ActiveMatter network is mainly to study self-assembly of active particles as well as understand the behavior that we see. The goal of my project is to develop dynamic, self-assembled structures that respond to external stimuli in real time. Therefore, we'll be using superparamagnetic particles. The particles that we use consist of porous silica with iron oxide dispersed throughout them. Due to the random orientation of the magnetic moment of the iron oxide, overall the particles, as illustrated on the left-hand side, will have no magnetic moment. However, if we place these particles in an external magnetic field, the individual magnetic moments of the iron oxide will align, and overall the particle will have a magnetic moment, and is therefore able to form ribbon-like structures. The goal of my project is to generate more fundamental knowledge about the self-assembly of these particles and hopefully develop new active materials. This will be done by taking the superparamagnetic particles and placing them in a 2D environment. Initially, if we don't expose these particles to any external stimuli, we expect to see a randomly dispersed sample, as illustrated on the left-hand side. If we illuminate the sample by light, we expect two kinds of self-assembly to happen. First, we expect to see an ordered structure. Secondly, we expect to see a disordered ordered structure. With that, I mean that there is a level of organization within the disorder. And finally, if we expose these particles to a magnetic field, we expect to see chain formation. My research will be conducted at the Soft Active Matter Lab, where I'll be working with this lovely bunch of people. This is actually a picture taken in our old lab. We just recently moved to our brand new lab, where we're still waiting for the optical tables to continue our research. I would like to specially thank my supervisors, Giorgio, Phil and Nuno. I would like to end my presentation with a few planned secondments at the end of my PhD. First, a theoretical model will be set up in order to increase the fundamental knowledge about the system. Second, machine learning approaches would be very useful in order to hopefully decrease the amount of excessive experiments that need to be done. And finally, controlling the active particles at an interface would be very useful for different applications like the formation of thin films. With that, I would like to thank you all for listening and hope you have a nice day. Bye!